Hey everyone, I'm Nick from Coffee Before Arch, and today we're going to be talking about how do you implement a histogram kernel in CUDA. Now, what's the kind of trick to implementing a histogram kernel that makes it different than what we've done in the past? And the main difference comes from the fact that in all of our previous examples, what we've had is threads that are working on independent data. So while they may read from the same elements or data structures, they don't write to the same elements or data structures. Now, why is this important? Well, this is important because what happens if two threads want to write to the same memory location at the same time? Now, this is tricky in GPUs, as if you just do it kind of naively, the way we normally write things to memory, you've got the possibility of missing some kind of operation. And so let's think about that with a little example. So let's say I've got a value in memory, and main memory that is, that say 0. And let's say we have two threads only that want to add 1 to this value, right? So they both want to read 0, add 1, read the value, add 1. So what we might expect is that, okay, well, these two threads both want to add 1. My final result will be 2. Now, a situation of events that could happen is one thread reads 0, another thread reads 0, then both the threads say write 1, right? And this is all happening locally within their cores. Maybe they're on different cores. And then both of them write their result back to main memory. Now, when they do this, there really is no ordering here, and even that doesn't matter. So what can happen is that 0 gets written to a 1, but then that other thread also wrote a 1, so it writes a 1 to main memory. And suddenly, what we were expecting to be a 2 ends up being a 1. Right? So we can stomp values like that in main memory or overwrite them with a value that we're not expecting. So how do we fix this? And the way we fix it is through atomic functions. Right? So atomic functions perform a read, modify, write atomic operation. Right? And what we mean by this is that it will read the value, it will do some modification. In this case, what we want to do is add 1, and then it will write the value back. But what it will make sure is that no other event has occurred in between that read, modify, and write. So we're guaranteeing that every single operation will occur in some order, right? So we don't guarantee which order, but it will occur in some order, right? And we won't stomp each other. So you can think of it as serializing a single location in memory. Now in this case, in our simple example, what will end up happening is thread 0 will write and add 1, then thread 1 may write 1 or add 1, right? And so we get 0 plus 1, and then 1 plus 1 is 2. Or it could be the other way around. So thread 1 could write first, and then thread 2 could come in, or thread 0 could come in and write. Right? So it doesn't restrict which order it happens in. It just makes sure that all of the events will happen. Right? And then all of the events will we're serializing a single memory location with this atomic operation. Right, so let's see how we do this with global memory. So we won't do a complete naive implementation of a histogram, but we'll do one that's purely in global memory. Right, so we'll open up histogram.cu. And as far as our host side code, it's fairly simple. We're going to be sorting a 2 to the 20 element list of characters. Right, so we've got 2 to the 20 characters. So these will just be letters A through Z, lowercase. And we just want to sort them into 7 different bins, right? And so the way we initialize it is just by setting it equal to the character A plus some offset between 0 and 25 inclusive, right? So A plus 1 will give us B, A plus 2 will give us C, and there's 26 letters in the alphabet, so we'll go ahead and add rand mod 26 here, right? So that will give us, every number A through Z, but randomly, right? Based upon this seed of 1 that we're giving it. Now in our kernel itself, in our host code, the way that we have it set up is that every single thread will bin a single element. Right, so we'll calculate our global thread position, and this will determine which element we actually bin. And then we'll have this alpha position. Now the alpha position will just be where inside of the alphabet does this letter lie. Right, so in order to find that, we have to remove the ASCII value associated with it. Right, so if we subtract A, what this number turns into is just going to be rand mod 26. Right, so it'll be a number between 0 and 25, and that's the way we generally think about an alphabet, right? We think of A as being index 0, B as being index 1. So in this case, rather trivially, all we do is get rid of this offset. That's the ASCII value. So the ASCII value of A is, I believe, 97. Right, so we're getting rid of that offset. And then we call this atomic add. Now here's our atomic function. Now our atomic add, we give it an address. In this case, we give it result. So result is it's an array of 7 bins that we have allocated in inside of GPU memory, right? And then we'll go ahead and index it by alpha position. So this is 26, or a number between 0 and 26, non-inclusive. So it'll be 0 through 25 inclusive, divided by div. Now div will just be the number of elements in each bin. In this case, the number of letters in each bin, right? So if we want to divide 26 letters into 7 bins, what we end up getting is 6 bins with 4 letters and 1 bin with 2 letters, and that's about as good as we can do with those constraints. So the last bin will only contain letters Y and Z, but the other bins will all contain 4 letters. So say bin 0 will end up having A, B, C, and D, right? And so when we divide it by div, which ends up being 4, right, this value that we get left over, which will be an integer, so it'll just get rounded down, that will be what index inside of result we are, right? Or which bin of the 7 bins. And then the second argument is 1, because we're adding 1 to this memory location, because each thread is sorting a single element. So all 2 to the 20 threads that we end up launching across all of our thread blocks, we'll go ahead and do this for 1 element. Now we have it in a for loop, that way we can launch fewer thread blocks than we have elements, or rather fewer threads than we have elements. And this is if we want to pack more work into each thread. And we'll look at that a little bit later, specifically with the shared memory implementation. So let's go ahead and let's see how this runs, right? So we'll do -o histogram, and we'll go ahead and, we did histogram, sorry. nvcc-o histogram.cu, right? And then we've got our executable, and then we'll profile it as well, just to see how long it takes to run. So it takes about 500 microseconds, and if we run it a couple times, we see that it's just about 505, 506 microseconds each run. Right, and so that's with this rather naive implementation where we just have blocks of threads that will each bin a single element. Okay, so how can we make this better? Right, and so one of the ways that we make this better is through shared memory, right? And it's through a strategy that we call privatization, right? So the issue with doing this in global memory is it requires us to do atomics on global memory. Now, in this case, what this means is that these global memory atomics can only actually occur on things in the L2 cache or in global memory, which means when we're doing an atomic operation, what we're saying is that the best we can do is hit on that value and write it in the L2 cache. Now, with privatization, what we say is, okay, well, I know I've got fast scratchpad memory. What if instead of every single thread block and every single thread updating a single data structure, which is our result bins that reside in global memory or in the cached in the L2 cache, what if instead they all updated their own local subhistogram, right? So for the 512 elements that each thread block will touch, they'll generate a subhistogram that will bin only 512 elements. Then at the very end of execution, they will, all combine their subhistograms together to form a final histogram. So what does this mean for us? It means we can take advantage of atomic operations on shared memory, which are much, much faster than ones that are going out to the L2 cache or global memory, right? So these are shared memory atomics, right? So in this case, we'll go ahead and go to shared memory, right? So here's we'll go ahead and remove this previous work, histogram.dat, and we'll go ahead and open up our kernel, right? So our kernel right here is our shared memory implementation. So how does it differ? So the first way that it differs is we have to allocate a little bit of shared memory, right? So every single thread block will allocate 7 bins, right? Because it'll store its own, result bins. Then we'll go ahead and initialize each of those bins to 0. Right? We have to make sure we're initializing variables before we use them. And then we'll go ahead and call sync threads here, because just as a reminder, we have to wait for these writes to shared memory to be complete before we start using them. Otherwise, we could wind up with some values that end up being wrong. But then this internal loop, this for loop right here, it ends up being the exact same. The only difference being the value that we pass to atomic add right here, this atomic function, ends up just being the value or a pointer to, or an address in shared memory instead. Right? The exact same operation applies though, where we just bin some letter that we read out from global memory. So what we're caching here in shared memory is not the values that we're binning. What we're caching is the bins themselves, because each element inside of that big array is only ever used once. What we're reusing is where we're putting the bins. Then we'll call sync threads to make sure that all of our atomic operations have completed, and then we'll go ahead and do this single write out to our result bins that reside either in the L2 cache or global memory. So let's think about the scale of the number of atomic operations we're doing in global memory now. So in the global memory version, we're doing all 2 to the 20 atomic adds in global memory. Now the ones we're doing in global memory will only end up being 7 for 7 bins times the number of thread blocks we launch, because each thread block will write back its subhistogram or its 7 bins. So it ends up just being 7 times the number of thread blocks, which is going to be a lot less, or a lot smaller than 2 to the 20. And especially as 2 to the 20 gets bigger, maybe it's 2 to the 30, maybe it's an entire gig of letters that we want to bin. Right, and so it'll still be much smaller. Right, so let's go ahead and get out of here, and let's compile this again with NVCC, and we'll run our profiler on it now. Right, and just as a reminder, we'll go back here to our global memory implementation. Right, and we'll go ahead and profile this again and compare the two. And what we see is our global memory took 506 microseconds, and our shared memory implementation only took 113. Right, so it's, over 4x faster by doing this in shared memory. Now we can still play some games though in order to improve the performance even more. Right, and so we can pack more work inside of each thread in our shared memory version. So let's go ahead and open up our code again. And instead of launching as many threads as we have elements, right, so we're doing in divided by threads, right, so in divided by 512, what if we launch a quarter as many? So what if we divide this number by 4? Right, so now we go ahead and compile this again, and we run the profiler again. So now our execution time is only 55 microseconds, right? So 55 microseconds here compared to, if we go back to the global memory version and we call the profiler on that, this is compared to our 500 microseconds. So now we've gone from being about 4x faster to being, closer to 8, maybe even closer to 10 times faster by packing more work per thread. Now, why does this work? All right, so let's just do a little experiment here. And let's take our global memory version, right? So we'll open up our global memory version of the code, and let's do the exact same thing. Let's launch a quarter as many threads. So each thread is now binning 4 elements now instead of binning 1 element. And we'll go ahead and compile this, and we'll go ahead and profile it as well. And we see that, well, it's about the exact same execution time. So why does this make sense? This makes sense because when we do this and we pack more work into individual threads in the global memory version, we're not actually getting rid of any global memory atomics, right? Every single binning of an element is occurring in global memory. When we decrease the number of threads launched by 4 inside of our shared memory version, right here, right, where we get 55 microseconds, what we're actually doing is we're saying, okay, these we're going to do a quarter as many global memory atomics, and instead those are going to be fast shared memory atomics. So we're moving the atomics from being global memory to being fast shared memory or scratchpad memory, and because of that we can get an even greater speed up. Right, so this just goes into the idea of packing more work per thread, especially if we're going to be reusing the same data structures. Right, so we're all reusing that shared memory result data structure here, and then we're just doing a single write of that subhistogram out to global memory. But that's going to go ahead and do it for this episode. There are other techniques that we can do for histograms as well, such as aggregation. So let's say we have a picture we're doing a histogram on, and we're looking at the different values that we're getting. Well, if we're in, say a region where all the values are very similar, well, we can just get rid of the atomic operation altogether, and we can just start aggregating the number of elements that are exactly the same without an atomic operation. And then as soon as we hit a different color, right, or a different value that would go to a different bin, we write that big chunk that we've already calculated without atomic operations using an atomic operation, right? So that's another way that we can handle cases where we've got a lot of similarity between our elements. Wouldn't quite work that well here when we've got a nice kind of even distribution. And we can even, display this using GNU plot, right? So here in our histogram.dat, our data file, we see our 7 bins, each of which has about 160K elements. And then our final bin, so this is the one that only had 2 letters in it because it got unlucky because 7 doesn't evenly divide 26, right? It has about half as many elements. So if we go ahead and use GNU plot, and we go ahead and we plot this data, right, histogram.dat, what we see is, we get this nice histogram here. We see that most of the bins 0 through 5 have about the same elements, and then the final one has about half as many elements as all the others, right? But that's going to go ahead and do it for this episode. Like I said, feel free to check out any of this code at github.com/coffeebeforearch. So we looked at CUDA programming today, and we looked at histogram. Feel free to check out any of the other codes, such as the matrix multiplication with cache tiling, our sum reduction optimization series, and working with convolution, or the optimized libraries. But I'm Nick from Coffee Before Arch, and I hope you have a nice day.